Okay, so here we are in Excel. We are going to do an example of the Lilliefors Corrected KS Test. Now, this entire document is available for download in the link in the description. I highly recommend downloading it. All of this math is already in here, so go ahead and delete some of these if you want to follow along, or you can just use it. The only thing is, since we are doing the Lilliefors, which uses the KS test statistic, instead of programming all of that, we are actually going to use QE Suite. So if you don't know how to get QE Suite, link in the description on how to get started with your free trial. It performs all of the normality tests we've looked at so far in Excel with one single function. Highly recommend using that, but this is still a great chance to learn. So let's get started. Okay, so the first thing that we're going to need to do is get our KS value. And if you remember, we're going to use the QE Suite function. So QE dot Kolmogorov Smirnov, and we're going to collect our data. Oops. And I'm going to say return as object and hide my graph. And then I'm going to say .ks. And what that's going to do is instead of returning the KS and the p-value as the Kolmogorov-Smirnov function normally does, it just returns the KS value. So now we are halfway there, and all we have to do is calculate the Lilliefors p-value, which is the entire goal of this video. So the first thing that we're going to do is we are going to use our p-table method, so p-value from table. Okay, so the first thing we need to do is get our KS values at this sample size. So we're going to say index, and we are going to say select this entire down to 50, and I'll explain what this 50 plus is here in a second, but first we're just going to select this. Okay, and then our row number is going to be n minus 3, and that's because we start at 4, so we want to get everything offset by 3, so that 4 minus 3 is 1. That is our first row there, and we are going to hit enter. Oops. And I forget we have to include this for the column number. There we go. That returned our entire row there for the KS value. Let's double check. 1315, 1378, 146, 159, 1848. And we have 146, 159, 1848. Awesome. So that is great, but you'll notice we have this 50 plus here, and that's because the p-value table given to us by a paper by Abdi that uses this. So this is the corrected table. So it took Lilliefors values and just made them a little bit sharper, a little bit more precise, and expanded it a little bit. It goes up to 50. And so we have these equations here, which are already plugged in for you, so don't even worry about it. And that works for any sample size above 50. So what we're going to want to do is we're going to want to use an if statement. So we're going to say if n is greater than 50, then we're going to just select this row. Okay, awesome. There we go. Nothing changed because our n is not above 50. Next, we are going to do this bool row here. And what that's going to do is that's going to tell us whether or not this value is greater than our KS. Okay? And actually, we want to do less than our KS. So if we say is less than KS, we get true. Okay, awesome. So I'm going to absolute reference that KS and then drag this across. And now you can see we know that these two are lower than, these are greater than. So this is our KS1, this is our KS2. So what we're going to do is we're going to say count if, and we're going to select this range, and we're going to say true. And now we have 2. So that we're going to use to grab our p-value. So p-value equals index, and then our array is going to be the p-values, our row number 1, and then our column number is going to be our inflection. So it's going to grab 1, 2. Yep, perfect. There we go. And then we're going to do something very similar. We're going to say index. Again, grab that. And then our row number will do 1. And then column number is going to be inflection plus 1. 0.15.1, awesome, looking great. And now our KS is going to follow that exact same format where we select the array of KS values, and our row is going to be 1 and then inflection. Great, KS2, again, pretty simple stuff, but maybe some functions that you aren't totally aware of yet. Super easy though. All right, and now inflection plus 1 to make sure we grab that. And now we're going to plug in our interpolation equation. So we know that that is P1 plus, and then we are going to do P2 minus P1 divided by K2 minus K1, KS1, times our KS value minus KS1. There we go. We have a p-value, and in here I'm going to select that. So the reason we did that is because we also want to have the ability to use our approximate value. So this was going to require just a little bit more work to write in these equations, but still not bad because we have all of those constants right here. Okay, so for our a value, we're going to open up some parentheses, and then we're going to say negative, open up some more parentheses, b1 plus n. Close that, plus the square root of, and we're going to say power, and this is b1 plus n squared minus 4 times b2 times, and then we're going to open up another set of parentheses, a lot of parentheses here, b0 minus power ks to the negative 2. Negative 2. Close that, close our square root, and close our numerator. Then we're just going to divide this by 2 times b2. All right, everything looks great. Hit enter. There is our a value. Okay, and now for our p, we are going to then take that. This is going to be a little bit longer, but it's C0 plus C1 times A plus C2 times power A squared plus C3 times power A cubed plus C4 times power A to the 4th plus C5 times power A to the 5th plus C6 times power D12, which is A to the 6th plus C7 times power of D12, which is A to the 7th, plus C8 times power D12, which is A to the 8th, plus C9, and you guessed it, times power of A to the 9th, and finishing off with C10 times power of A D12 to the 10th. Enter, and there is our p-value. So let's put that in here, and look at that. As we said, it is only accurate to that second decimal, that hundredths place. So if we were to round this, we would get 0.11. And that's what we mean by it's only accurate to that decimal place. As you can see, it at a low p-value can be kind of risky as to whether or not you would correctly reject the null hypothesis. So definitely make sure that you're using the tables when you can. So this use approx we'll get to in a sec. But first what we're going to do is we are going to make sure that we can select between them. So we're going to say if we use the approximate method, then we're going to use the approximate p-value, else we're going to use the table p-value. And right now we don't have, we're not using it. If I were to type in true, true, there you go, it would switch. So now we want to add in some logic that allows us to use this down here to select between the two. So if you remember, we're going to write an if statement. If you remember, we want to make sure that we use the approximate if it is lower than any of these values. If it's greater than the 0.01, we're just going to call that 0 because in that case, you know, that is such a low p-value, your data does not follow the normal distribution. You just have to accept it at that point. And approximating your p-value, you will end up with negative values because you're only accurate to that 0.01 anyway. So it's useless above that. So we're going to use it if it's below. And so if our value is below this 0.2 KS value, we're going to get an inflection of 0. So we're going to say if that equals 0, then we want to return true. Because if that's less than 0, if that equals 0, then we need to use the approximate value. Else we're going to give it false. And there we go. Now if we were to have a KS value, like let's just use that one from our example, 104.165, we end up getting our p-value from the approximate. We get a spill error there, and that is just fine. No harm done. Okay, I'm going to undo that, and there we are back to normal. Okay, but let's say you don't want to go through all of that hassle. We're going to use this, equals QE dot Lilliefors test, and we are going to select our data, hide our graph, and there we go. Just like that, in seconds we were able to do everything it took us about 10 minutes to do. But that is the Lilliefors Corrected KS test. Soon we will be talking about some comparisons of these normality tests, and we'll really dive into why anyone would want to correct the KS test anyway. So thank you so much for watching. Have a great day, and please do something awesome.